So let's meet the objects we're going to talk about. Let's meet vector bundles. So the idea is, roughly speaking, that a vector bundle on a manifold M associates to every point of that manifold a vector space EP, and it does so in a sort of smooth and coherent manner. What that means precisely is a vector bundle over M is a manifold E equipped with a morphism pi going from E to M, and now we want sort of the fiber of every point to be a vector space, and again in a smoothly compatible manner. And what does that mean? Such that there is a cover UI of our manifold M and isomorphisms phi I going from, and now we want a subset of E, namely the image of UI under what's called the bundle projection map to UI times R to the N, such that these isomorphisms are compatible in a way. So we have on intersections, we can map pi inverse of UI intersected with UJ. We can use phi I to map that to UI intersected with UJ cross R to the N, and we can use phi J to map it to that. Well, technically this could be different, but we want that these isomorphisms play nicely together in a certain way, such that this map psi ij, I guess, can be described as psi ij of a point in the manifold together with a vector is equal to that same point. And now we have a function gij of p times v. And what is this function gij supposed to be? Gij from ui cap uj to the invertible n times n matrices, such that this map is given this way. This means that these isomorphisms are sort of compatible in the way that they leave the points, they map the points just to the points, and they act linearly on the vectors. This gives every fiber pi inverse of, well, the set containing the point P, which we usually call EP, a unique vector space structure. And second thing, a morphism of vector bundles pi from E to M and pi prime from E apostrophe to M is a smooth map. Phi going from E to E apostrophe or to E prime, such that if we draw the commutative diagram, or if we draw the diagram E goes to E prime, pi prime, that this commutes, and we want another condition such that if we restrict phi to one of the fibers, well, by the first condition it restricts to a map from EP to E prime P, and we want this to be linear. And I guess it's easy to see vector bundles and bundle morphisms form a category. Notably, I'm talking about vector bundles over M, and their bundle morphisms, they form a category, and I'm going to call that one Vect M. Now there are a couple of very interesting constructions. Notably, you can port almost every sort of functor you can do to finite dimensional vector spaces to vector bundles. If we have, I guess if E and F are vector bundles, then we get vector bundles E direct sum F. Well, we define the fiber in any point just to be the direct sum of the fiber of E and the fiber of F. And then we can define a tensor product where we do this definition on fibers, or where we do similar definition. Then we can do a dual bundle. We define the fiber in every point to be the dual space of the fiber of the original bundle. And lastly, and also importantly, we can define the Hom bundle from E to F, which just in every point has linear maps from EP to FP. And of course you would need to check that you can sort of give all of them the structure of a smooth vector bundle as mentioned in the definition, but you will ultimately find that this succeeds. There's this Hom construction, which is quite important, and I'm going to cover that now. Another important definition pertaining to vector bundles is, well, what can you actually use them for? Sort of objects that inhabit those vector bundles. Let pi em be a vector bundle, a section of E is a map usually called S from M to E, such that pi after S is the identity on M. Put differently, it is a smooth map satisfying that for every point S of P is an element of the fiber over P. And yeah, I guess that's a lemma. These sections, we call them the sections of the vector bundle E over M. And our lemma is EM is a module over the smooth functions from M to R. Yeah, I guess we can just define the operations. If you have a section S and a section S prime, you can add them just by adding the values that they take in a point P. You can add those values because they are elements of the same vector space. Then you can scale them by a number, so that makes them into an R vector space, but that's not everything. You can also scale them by a function, and that is just f of p, s of p. So all of the operations are just defined pointwise, and that makes it into a module, and it's a big theorem that firstly, those are not any kind of module, they are projective modules. But not only that, so projective modules over C infinity m, but they are in fact all projective modules, meaning that if you have a projective module over C infinity m, it will be the sections of some vector bundle. And another thing in this theorem says that, or I guess it's a corollary to that theorem, every bundle morphism phi from E to F generates a section, I guess S, of the Hom bundle EF, a global section, and vice versa. So the bundle morphisms between two bundles are just the global sections of the Hom bundle, which, I mean, in a way is just switching the order in which you insert points and vectors. And yeah, the last construction I need to cover is the construction of pullback bundles, which I guess started this whole endeavor. So we have a vector bundle on M, and we have a smooth map from another manifold N into M. Then we define what is called the pullback of E by phi to be, well, in terms of manifolds, we take the fiber product N times E over M. This is a vector bundle over N, now called the pullback of E. And it is sort of this construction that makes the functor Vect really into a functor, because together with this pullback bundle we also have another construction. Let S be a section of E. Then we can define phi star S as a section of phi star E and N. So it should be a map from N to phi star E. What does it do? It maps upon P and N to, well, the point itself should lie over the point P. So we have that, and then what in E? Well, that's just S of phi of P. So now I'm claiming Vect going from the opposite category of manifolds to small categories is a fibered category. So we need to establish that firstly it gives us categories, secondly it gives us functors, thirdly there's a natural transformation, or there are two natural transformations that make all of this work. So firstly, Vect M is a category for any manifold M. Yes, we have already seen that. Secondly, for phi from N to M smooth, we have a functor Vect phi going from vector bundles on M to vector bundles on N. And what does it do? Well, if E is a vector bundle on M, then it just creates a vector bundle on N by the pullback construction. Okay, this is what it does on objects, but what does it do on morphisms? Let F from E to F be a bundle morphism. What does it do? Well, it first maps this thing to a section of the Hom bundle, E to F. Then it maps that one to the pullback section. That is now an element of the pullback bundle. E, F, N. And the pullback of the Hom bundle is isomorphic to the Hom bundle of the pullback. So we have phi E, phi F. So that thing can now be mapped to the pullback F, which is a bundle morphism from phi E to phi F. I guess it's not that hard to check that, like, this is satisfied. Similarly, the same thing with the identity. So we have this pullback functor. So now do we have a natural transformation for the composition of two pullback functors? So let psi from L to N, phi from N to M be smooth. Then a natural transformation acts between objects, so for a bundle E in Vect M, we have Vect phi after psi of E, well, that is just phi after psi star E, so that's the fiber product of L with E over M. And conversely we have Vect psi of Vect phi of E, that is psi star of phi star of E, that is psi star of N fiber product over M E, which is L fiber product over N with N fiber product over M E. So that is the objects PQV in L cross N cross E, such that psi of P is Q and phi of Q is phi of R. But if we have an element here, PR, we can just map that one to P psi of P R, and that one is an element here, and this is an isomorphism, and it turns out to be natural. And I guess for the identity functor, we can note that the pullback of E by the identity is just M crossed with E over M, and we can map that one to E just by having point and vector mapped to the vector, just because we know that pi of R is equal to P. So that is our natural transformation psi phi inverse, I guess, and that is our natural transformation U E inverse. and ultimately you can check that these are indeed natural transformations, and we find Vect is a fibered category.